This video is going to go over the concept of buffers and pH, beginning with the definition of a pH buffer. pH buffer is a chemical system that resists change in pH. I'm going to emphasize this a couple more times during the video. pH buffers don't prevent change in pH, they fight it, they resist it. They take big changes and make them into smaller changes. Every pH buffer exists as a conjugate acid-base pair, a weak acid and a weak base together at chemical equilibrium. Now, as you watch the rest of this video, if you find it confusing, you may want to jump ahead and view the videos on chemical reaction from the energy series of videos. It will probably help you make more sense of this. But I'm going to plow ahead right now, and again, if you're confused, go watch the chemical reaction videos first and then come back to this one. A strong acid, or a strong base, is an acid or base that is fully and irreversibly dissociates when it hits water. Okay, if the acid completely falls apart or the base completely falls apart, donating its hydrogen ion or its hydroxyl to solution, it's classified as a strong acid or a strong base. Weak acids and weak bases, on the other hand, reversibly dissociate when added to water, meaning the acid will donate the proton, but it might take it back under the right circumstances. Weak acids and bases, when reversibly combined, resist change in pH, and the result is a pH buffer. So we need weak acids and bases to make a pH buffer. Here is a very important biological buffer system, and this is one you really want to know because it comes up a lot in human biology. In this chemical reaction, we have carbonic acid in a reversible equilibrium with bicarbonate and a free proton. Because the carbonic acid is forming the bicarbonate and the free proton, it's donating the free proton, it's the acid. Because the bicarbonate ion is combining with the free proton to form the carbonic acid when the reaction proceeds to the left, the reality is it's a proton acceptor and it's a base. And so here's sort of a way with ball and stick models of illustrating this buffer system. You want to know this chemical reaction. You really, really want to know it. Now, let's take this chemical reaction and look at it in a real setting to understand how a buffer works. So here we have a system with 5 protons present, 5 hydrogen ions present in this system. And I've just added more. Acid has been added to the solution, so the number of free protons has gone from 5 to 9. And what we're going to see some of the bicarbonate ions in here do is interact with those extra protons to form more carbonic acid and bring the number of protons back down. Now notice it didn't go all the way back down to 5, it dropped to 7, but 7 is closer to 5 than 9 was. In other words, it reduced the size of the change in pH. It prevented it from being as big as it could have been. Acid added to a buffered solution still decreases pH, increases hydrogen ion concentration, but not as much as it would do so in the absence of the buffer. By contrast, here's our same starting solution with 5 protons present, and I'm going to add a base to the solution and take out some of them such that the number of protons has dropped to 1. In this situation, some of the carbonic acid molecules will dissociate to free up some extra protons. Now again, they've acted as proton donors. The number of protons is still lower than it was when we started, but it's gone to 3 instead of to 1. When a base is added to a buffered solution, the pH still increases, hydrogen ions concentration still decreases, but not as much as it would do so in the absence of the buffer. Weak acids or bases are those acids and bases that reversibly dissociate when added to water, that don't completely accept or donate protons, and a pH buffer is the chemical system in which we get a conjugate acid-base pair together to resist change in pH, with one of the most prominent pH buffers used in the human body being the bicarbonate buffer, in which carbonic acid, the weak acid, dissociates to form bicarbonate, the weak base, and a free proton, reversibly so that bicarbonate and the free proton can combine to form carbonic acid. You should know this chemical reaction in my classes.